Okay, thank you very much, Professor Riedel. It's a particular honor and pleasure to address you today with a topic which I think is not only almost weekly in the news, you might even say daily in the news, but which has a transformative and disruptive effect on many parts of our human society, academic life, industry, and so on. So I like to have a title which is slightly provocative, machine learning, a paradigm shift in human thought. And you might even translate this into, okay, let me see, into the question, Quo vadis artificialis intelligentsia? And this is already a product of AI because Google Translate translated it. I probably would have been able to produce that by myself, but you know how much Google Translate has influenced our interaction with text. So the world in which we live is a world of data. Here you have the background fluctuations of the microwave background. You have here some data from the medical realm, MRI data of one of the great uncharted territories, how our brain works. And we used to develop machines, computers in the 50s, and here the CSCS Lugano in 2018, which allow us to extract from these data some value. And the essential communicator between the data and the value are algorithms and their implementation in software. So I would like to stress in this talk that algorithms have a far more critical and pivotal epistemological role in this business than we might have given them credit so far. Now let's start with the data. So the picture is in reference to the new Nobel Prize in Physics. It shows the center of the galaxy, and it also shows that we quite often manipulate our data and make them interpretable. So the black spot in the middle is not actually a measurement, it's an artist rendering of pointing out where the black hole is suspected. So data are observations of reality, if you believe in reality, and they give us shades of what we can observe. Now, my own area is focusing mostly on applications in medicine, so let me give you a little bit of a view. You have data of very different types. On the left, you see gene expression data for diseases. You see mass spec data, so these are sequence data. In proteomics, in metabolomics, you have images, this tissue microarray, which tells you about the histology. Here you have serial section transmission electron microscopy images from brains. And here you have a data format which is quite modern, the connectome of the brain. And from all these data, you have to sort of extract information and get interpretations. But you have more data. The human is a very important player in medicine. So you get data annotations for diagnosis, prognosis, and therapy. Here you have my lab data, and this is the report for my cardiologist. So all these type of data should play a role and have to be sort of fused to a final view at things. Even more, we measure ourselves more and more in terms of quantified self, so with these Fitbit devices, and we mostly ignore all these data, and we should make more sense out of it. Now, data gathering is not a new activity. So you see 22,000 years ago, humans carved information in these bones. So the Shango bones seem to be one of the earliest documents of data gathering. In antiquity, the Library of Alexandria was famous as a place of knowledge, information put together, and people studied that. In the Enlightening period, we experienced the pressure to get better insights into reality. So these are the burial tables which have been analyzed by Gowns for the first time. So it's an old tradition to document what we observe. So with digitalization, what has actually changed? What's different to analog times, and what's our benefit? Now, I would say, boldly claim that what is different is that it gives us control by algorithms. And this is important because that means that we can discover models, we can test hypotheses, find solutions, and taking this together, you might call this intelligent thinking, or if you are more cautious from a philosophical point of view, you might at least credit that these are traces or shadows of intelligent thinking. So let's talk a little bit about algorithms. I would like to characterize them as giving us relations between data, so our perception of reality, and the decisions we want to make. So deduction and induction are two strategies to generate knowledge. So deduction starts with axioms from core principles. Then you use mathematical modeling or thinking. I like to use these now synonymously here. And from the theory up here, you derive facts. So this is deduction, and it goes back to Aristotle. Now, where do these axioms actually come from? You have to convince yourself that they are adequate for what you want to conclude, so that they actually lay a foundation. The opposite direction is induction. You use empirical modeling or empirical thinking to deduce from observations then the general laws. And so this cycle, deduction and induction, that is what drives our quest for creating knowledge in an intelligent way. And it goes back to actually Leibniz, who first stated, as far as I know, and I basically follow Bertrand Russell's book, The History of Western Philosophy. There, he characterized both deduction and induction as computational processes. So the first mechanical calculators were envisioned at that time. He invented the binary system. A formal description of the computer was then laid down by Turing with his universal computer. And new facets to this computing challenge came with quantum computing. And I like to reference Richard Feynman as one of the protagonists in this research direction. So that's computational modeling and thinking. And I believe the mathematical modeling and thinking, the empirical modeling and thinking, and the computational modeling and thinking span a huge area of thought, which we can fill now in and explore. So in personalized medicine, let me now show what this algorithmic processing means. You start with possibly terabytes of data. You annotate them to produce information. What you then do is you produce knowledge out of these information bits. You abstract it. Here is a pathway for clear cell renal cell carcinoma, a very deadly kidney cancer. And then you produce a value. And as I usually say, it's not the smile on the face of the patient, that's also a value, but the value you are interested in is this. It's a Kaplan-Meier plot, which tells you what is the probability of survival as a function of months. And these bits, which are in these two curves, the green and the red one, with the prognostically better, the green one, and the prognostically poor, the red one, these bits are decisive for quality. If you want to manage your life in such a terminal disease, then it makes a very big difference whether you are exposed to chemotherapy and it actually has an impact on your disease development or not. So this reduction of information from a terabyte of observations down to possibly kilobytes or 10 kilobytes of resulting decision-making knowledge, that reduction is governed by hundreds of algorithms with even more parameters. So how can we actually tune these algorithms in such a way that they extract the correct bits? And let's be clear here. Doctors cannot tune these algorithms. This is something which has to go automatically. And Thomas Fuchs, a PhD student in my group, he's now a professor in New York, has a company, Page.ai, which used this concept of computational pathology essentially to leverage this knowledge. So from an abstract point of view, what I like to advocate is these algorithmic pipelines with possibly dozens of algorithms in, it establishes a probabilistic mapping from the input, your biopsies or your measurements on the disease status, to your output, the survival probability. And you might even intervene, and then you have drugs and treatment in the loop, and you still want to influence the survival probability to the benefit of the patient. This is the object which we have to estimate. Now, let me refer to what algorithms are in order to make the point where we have sort of new facets now. Here is the informal definition. An algorithm is any well-defined computational procedure that takes some input value and produces some output value. And this goes back to one of the leading textbooks in that area. Here you have the algorithm used by cardiologists when you have a heart attack in 2015. Just to refer to something. And you also see there are terminal loads, color-coded, one here, here, and here. So analysis of algorithms so far has concentrated on runtime, memory shortage, energy consumption, and possibly other characterizations of the algorithm. But we clearly fall short of algorithm robustness and the generalization ability of algorithms. In some settings, it's not even clear what we mean by that. And I would like to address these two things, these two properties, robustness and generalization ability, because that's essential in applications that you trust the algorithmic pipeline as being a validated model of what you want to extract from reality. So learning algorithms explore reality, and I would claim it's a complex stochastic reality which has deep problems in terms of how we look at algorithms. So here is a more, an even newer flow chart of these ACTS algorithm, just to see that there is progress. Now, extracting value from data, what is the problem? The fundamental problem I see is the following. Algorithms that process input with noise compute random variables as output. And input with noise is something which happens in very many applications. Even the user quite often is a noise source when it inputs something to the computer. So how can we prove correctness of our algorithms when the output variable is a random variable? Shannon taught us that algorithms should compute typical solutions because typicality is a property which you rely on in communication. And with communication, I think we have the far more general concept of decision-making there. Then Wapnick showed in the 60s that algorithms have to generalize, and they have to generalize both over model misspecifications, so that's the noise, and possibly also the wrong models. So how should we regularize algorithms to foster this robustness? And that is necessary to understand how algorithms can autonomously improve their performance, which ultimately is the holy grail of artificial intelligence. So the hope that this actually is solvable comes from biology. Learning machines master algorithmic induction, and we try to imitate humans, and the humans with their brains have great generalization and theory building capabilities. So artificial neural networks in the 90s mimicked such an architecture by basically abstracting very significantly in terms of a feed-forward processing pipeline here. So this was good for recognizing zip codes. This is good deep face for recognizing faces. And it seems to be one of the leading face recognition algorithms, apart from those which are secret and under government control in various countries. If you want to know what these deep networks now do, what they actually store, you can let them hallucinate. And here is a video which I received from Sebastian Novotny in 2016. You see blurry images which remember of scenes with objects. This is the state of the art in 2019, when you actually morph from a cock into a wine glass and back. It also works on flying objects, as you see here, going from a balloon to a fly in various different ways. And here you see research from a PhD student in my group looking at high quality reproduction of faces and actually morphing faces of different people. So these are between females. You can also change the gender. When you interpolate, for example, here, you go from this face over to this face, and you might judge by yourself whether you believe that the face, the algorithm which captures the essential of these faces stays in the subspace of face-like images. And I think there are still some deficits there, but I think this is a great improvement of the technology. Now, if you have all these algorithms, how can you make sure that they actually do what you like them to do? So the validation of algorithms for me is one of the key concepts, in the same way as the validation of models in mathematics was the key justification, whether you can consider them as sort of an abstraction of what you think is reality and how you then can make predictions. So the autonomous predictive model inference, that's the key challenge which we have to solve today. Now, abstractly speaking, I told you already, random inputs imply random outputs. So we have some measurements X, and it's drawn from a probability distribution for the sake of abstraction. Here, these are gene expression data. Then you convert these gene expression data in a matrix, in a correlation matrix, and you represent it as a graph. And then you ask for algorithms which interpret these graphs with the weights on the edges. And in this particular application, we were interested in gene clusters. So you want to have a coloring of that graph. And here you have different solutions of these colorings. So that's the challenge. And you should actually appreciate that the output, and I denote the output with C, that the output should be drawn from a posterior probability distribution of the solution given your observations X. So this is the posterior, which I showed you already in the context of the information technology value chain of personalized medicine. So which algorithms now to choose? Don't hope that the user from the application areas will tell you what the correct algorithm is. We as computer scientists have to solve this problem. And you see you have epistemic uncertainty on the input and you have aleatory uncertainty on the output. So uncertainty is everywhere. Why is that a problem? Now, outputs of machine learning algorithms are random variables. And so the correctness is a critical question. So imagine now, for simplicity, an example which you can easily follow. I take a biased coin, I flip it 1,000 times, and maybe I even tell you that head has a probability of 60% and tail of 40%. So which sequence do you want to report? Think for a moment. Do you want to report the minimizer of the negative log likelihood, which is the maximizer of the likelihood, which is the most likely sequence? Or do you want to sample a sequence? The problem is, and that's what we know from information theory, the most likely sequence is an all-head sequence. And it's atypical. You never observe it in reality, at least when the sequence is long enough. So in some sense, when we solve real-world defined linear integer programs, integer linear programs, that's exactly what I just ask you to do here. Which sequence do you want to report when you minimize the negative log likelihood? We give the wrong answer because we commit to one and only one solution, and we should actually perceive that the knowledge is not in that one most likely solution, but in the ensemble of solutions which are typical. And the most likely solution in this context is not typical, so it should be avoided. Let me now advocate what I believe in which direction we should go to get these learning problem, these inference problem for robustness under control. You conduct an experiment and you conduct its control experiment, and this gives you two different data sets, X prime and X double prime. And now you have to calculate the posterior as I motivated earlier. You have to calculate the posterior for the solutions given the probable data X prime and X double prime. So here is the posterior for X prime. It ranks the different solutions C according to how probable they are. Here is the posterior for X double prime. Since C is a random variable, we will integrate over it or sum over it. And that gives us a kernel which tells us how similar X prime and X double prime are in the light of the solutions which our algorithm extracts from these data. So we are not measuring the similarity of X prime and X double prime in the sense of an abstract metric in the input space, but we measure the similarity with respect to the algorithmic effect on the output space, on the solution space. That's basically what we care about. How similar are two Kaplan-Meier plots with survival probabilities given two measurements? That's the question we are interested in. So if that kernel is too broad, if the posteriors are too broad or too narrow, then the kernel value will be low. And somewhere in between, you have the right trade-off between stability, which favors broad kernels, and precision, which favors very narrow kernels. And so my claim is that the optimal posterior essentially calculates the mutual information between X prime and X double prime, and this is the formula which we have explored so far. And here you have a graphical setting of these posteriors. You have the blue posterior on X double prime, the red posterior on X prime, and you see for various different width parameters of these posterior, you either get a small kernel value, a maximal kernel value for the middle choice of this beta parameter, or again, a small overfitting value of the kernel for a too high parameter value. And beta, if you like, can be associated with probability distribution, with the inverse temperature of a Gibbs distribution. So if you are interested in sampling procedures like simulated annealing, then this beta would actually parameterize the time you use the sampling algorithm. Now, if we now have this technology, what is missing? What is missing to really build algorithms which are intelligent in that sense? What is missing is the scientific method. So when you remember the scientific method, you ask questions, you propose hypotheses, you conduct an experiment, you analyze your results, and then you go back to your experiment and you improve it to learn more and more about reality. At one point, you are actually bold enough to postulate a theory, and then you ask fundamentally new questions. And you go through this cycle as long as it takes, and Galileo has first formally described this process and sort of founded the scientific method for exploring natural science, but also in engineering science and so on. What has changed with the advent of computers that now we have algorithms at all of these arrows. These algorithms better be validated in order to make this whole process work. But if you have a validation technology for algorithms, machines can learn these algorithms autonomously, validate them, and then make these deus ex machina, these enabling principle to generate new knowledge. And that's exactly what I believe is the success of science. A scientist doesn't need a teacher to make a fundamentally new discovery. A scientist needs a process which self-corrects and guides himself or herself to the truth. Now, what does that validation of algorithms actually mean? At a very high level, I like to distinguish three different settings. One is, the first one, humans know how to solve the task and you want to automate it. There is an enormous history of algorithms design and engineering and procedures which can foster that. So I think this is conceptually well, it's well explored. There is a lot to be done today at that level, but that's sort of not my concern. The second category is humans can solve the problem, the task, but they don't know how. So this is in some sense the crisis of expert systems. So what you then can do is you take the humans, you use them as a teacher in a supervised methodology. You mimic that human expert, and our success in terms of classification algorithms goes back to this mode, and in particular the deep learning excitement comes from spectacular successes in supervised or self-supervised settings for density estimation. The third question is humans can't solve the task either at all or not good enough. Then I see two extreme situations there. You can pursue autonomous learning by self-play, and AlphaGo 0 is exactly such an approach. The Go game has sufficiently simple rules so that the computer can emulate its own teacher and play against itself, and then systematically explore good strategies how to crack this game. Life has no simple rules. So the second challenge is the unsupervised learning. And here we go back to our scientific method. It's reproducibility and informativeness, which have to come together and which actually explore this trade-off between good experiments, which allow you to make fine resolution of solutions, and not so precise experiments which only give you a coarse overview. That is the technology I see still missing in artificial intelligence, and which has to be explored in the future. So here is again my personal bet on this challenge to validate unsupervised learning algorithms when humans actually can't solve the task. Let me now give you two examples of this technology, one in the context of a science which was always very proud of inventing their models. So I report on a joint project by the astronomer Refregier from ETH and Thomas Hoffman, my colleague in computer science. So you have the universe here. And this is the time evolution from the Big Bang of the universe. So what you see today is a projection of the light which reaches your telescope at a particular time point. So that's the observed density. What the cosmologists now do is they take these data and they want to interpret them. And in particular, they have simulators built, extremely complicated simulators, which are fed with cosmological model parameters. And then they actually can simulate observations. So these are now hallucinated observations based on the knowledge of a simulator fed or controlled with certain model parameters. Which of the simulated densities comes closest to the observed one? So that's the challenge here. And these are all random variables coming out, because even in the simulator, you try to simulate the randomness. So concretely, they had 600,000 images and a couple of observations. So what did they do? They used the simulated densities as sort of witnesses for the cosmological parameters they used for the simulation. And then they analyzed the simulated densities with a deep neural network to extract some summary statistics here. So the network encoded a probability distribution of simulated summaries given cosmological parameters. With that probability distribution, you now could do inference. So you use Bayes' rule, you convert the likelihood here of these simulated summaries based on your observations, which are these simulated densities here. You convert it into a posterior of the probability of the model given the data. And then you can ask the following question. Given this inverted model, the posterior, what is the probability of the cosmological parameters given the observed density? So now you can answer a question using a computer program to actually abstract your very complex setting of your simulation in order to estimate what is the most likely setting of cosmological parameters. And I find this remarkable because in one of the purest sciences like physics, you have a complexity which we partially ignored, but which is now accessible with these types of tools. Let me now come to big data in neuroscience. I have worked on these different resolution scales, microscopic, mesoscopic, and on the right hand macroscopic. And let's concentrate on the mesoscopic scale. Again, we have there a pipeline of data processing units, you have scanner parameters, you have diffusion weighted images, then you construct your diffusion tensor per voxel. These diffusion tensors give you information about the direction of the fibers, you do your fiber tracking, then you get a connectivity matrix down there, and you want to group the connectivity matrix now with some grouping principle, which we also don't know, and extract a minimalistic structure, which you then can project back on the surface of the brain. The neurologists told us that this information is valuable. I don't want to dispute that, but at least this was the formalization of the pipeline. And Nico Gorbach undertook this challenge. Here you have a rendering of the biologist setting in abstraction, and here you have the computer scientist graph theoretical rendering, so that you see there is an abstraction going on from biology to computer science. So what we now do is, we now simulated our inference principle. And what you can see is, on the left, the information content extracted by the self-validating algorithm. In the middle, you see the dissimilarities between the centroids, which means the areas carved out on the brain and then projected on the left-hand side on the brain. And when you go through this maximum of generalization, you see that the boundaries of these areas become fractal on the left-hand side here. And this sort of fractionated behavior is exactly an indication that you overfit and you can't trust your results anymore. So at least this shows that for this type of application where no biologist can actually tell you how to validate this data, you can do this in an automatic fashion. Now, the second example which I like to show you is from cardiology, interpretable artificial intelligence. We want to learn a digital heart model. So we have all this input data. We have a digital heart model here. What we are interested in is not a precise physics rendering of the heart and its dynamics, but an abstraction in terms of the shape. So we go for a deformation model here in order to extract a morphological parameter of the dynamics of the heart with respect to possible cardiological diseases. So you can now synthesize from such a mesh your data, both echoes and ECGs. But you can also measure these echoes and ECGs. And the comparison between what you synthesize and what you compare, what you measure, this difference, you take the difference, allows you to improve your deformation model. And then you consult with the experts for validation. You use machine learning, and hopefully this triangle there, machine learning and the expert validation, gives you diagnosis, prognosis, therapy, outcome, and risk stratification. So that enables you to tap into the value chain of medicine. And how far are we now? So this is the beginning of this enterprise. Here you see a 3D shape measured by MRI and abstracted. And you pump this shape through a deep neural network. You construct a compressed representation, and then you decompress this again to reconstruct it. It's different, but you can use this difference between the simulated heart and the measured heart via a classifier, a neural discriminator. And if the neural discriminator clearly distinguishes between the synthesis and the measurements, then you get an error signal and feed it back. You do the same for echoes. Here is a synthesized echocardiogram. And the feedback of this information is then used to adapt these parameters in these deep neural networks. Now, in this context, we have now two different views at the heart, and you hopefully would like that the compressed representation in these two networks are not completely independent. So you couple them to each other so that one modality can help the other one. So that's sort of an indication where this technology will go, and hopefully then it will have an impact on better diagnosis. So let me now come to a point which at the end might be interesting to some of the users, artificial intelligence and ethics. There are a lot of problems there, or let's say not problems, there are challenges because everything has changed. So we actually have to go back and reconsider our values in the light of that new technology. Last year, you saw this headline in the NZZ, algorithms are very dangerous. I thought already like a firefighter, I get now a raise for dangerous work. This year, you have this death algorithm book and the discussion about it. Why do we need this technology anyway? It's because of this chart. So from Alessandro Curioni from IBM Research, I got this chart, which actually was an eye-opener to me. The causes of death in the US 2016 are listed here. Most die of heart disease, cancer, but down here, very tiny, you might not even read it, it's terrorism, around 0.01%, so a tenth of a promille. This is what people are interested in. That's what they look up in Google if you make this abstraction. You see, nobody is concerned about heart disease because we know that burgers are not good for your health. Cancer is still an issue, so they look for it, but terrorism has dramatically captured more attention. And this is what the newspapers are reporting on. So if you see how grossly misjudged are the probabilities of the danger relative to their exposure in the media, I think we need intelligent technology to redirect ourselves a little bit, because we by ourselves are not able to do that. That's one of the reasons why we need, in this super complex world, tools which guide us in our decision making. What are the dilemmata of artificial intelligence, as I like to put them together? It's privacy versus personalized services. That's not only in medicine, but also in many other types of applications. That's a dilemma. There is the material concept of a value, and that's the immaterial concept of a value. These are different. Autonomy by learning and legal responsibility. Maybe you have seen the MIT moral machine experiment. 25 million situations like this have been simulated and sketched, and users, people have been asked how would they react. would you actually, if you can't brake, would you run into the two elderly people or in the woman with the kid? These types of situation in a forced choice experiment may give you an indication how people think about moral value. And quite interesting results have been derived from that. I know it's all questionable. Forced choice manipulates our thinking, but maybe it still gathers a little bit. Plausibility and algorithmic complexity. Do we believe that we understand in a deep neural network with 120 million parameters, that's the phase synthesis from the student in my group, do we believe that we understand how it comes up with the right decisions? I have my doubts. I think this is out of question. We cannot find the usual explanations how it works. And then there's all these issues with prejudices and fairness. So I would like to stress that algorithms reflect the information in our data. What should we do if the results are ethically questionable because they reflect our behavior? Who has the authority to fake the data for politically correct fake news or fake intelligence? I think it's a fundamental dilemma which we have avoided so far because it wasn't a real problem. But with the scale and the impact of this technology, it becomes a problem and we have to find new solutions to that. I'm not saying that I know the answers, but I think it's very clear we all have to think about that. Data security and personalization. So who does own the information about me? For example, my genome, me, my parents, my sister, my children, my health data for diagnosis, prognosis, therapy. Am I owning it or the attending physician, the insurance company, the lab? It's not so clear because many of these data are actually relational data. In a diagnosis, my biopsies in conjunction with the knowledge of my physician is generating the data. So this is a complicated situation which we have to rethink because I think we have not yet found a legal basis which is flexible for the future. So personal rights versus common welfare. I think this is an issue which completely differently comes up in this new technology. So what are the lessons learned and the challenges ahead of us? I hope I could convince you that algorithms model posterior probabilities of solutions given data. So in some sense, the quest of mathematics to build models is now expanded in scope and in particular in complexity by computer science and our characterization of algorithms, which are actually representatives of these posterior probability distributions. And if you don't believe in probabilities and you want to have an inference setting with fuzzy logic or something more general, I think the situation with respect to algorithms will not change. It's the calculus which slightly changes, but not the epistemic setting of algorithms as the mediators between the data and our final decisions. Learning requires the validation of these algorithms. That's the key thing. Humans are no longer inventing the models, they are controlling the models. And we have to find the right control strategies. And we have to control algorithms even if we might not understand them in detail. And when you look at how chips are validated today and the programs behind the design of it, then you see already that, that this is practice in how we conduct our business there. So the real epistemic challenge is how can algorithms extract structure-specific information in the data? And with structure-specific information, I mean that the values set by humans in medicine, for example, to extend the life expectation is one setting. Another setting is that you say, no, I'm not trying to live as long as possible. I am trying to have a high life quality as possible. So this is a fundamental decision, which I believe is depending on the user, and the user is a human. having made a decision about this goal, I think the algorithmic adaptation has to pay respect to that decision and then starts to optimizing. And it relates a very deep mathematical problem. How does statistical complexity, and that's basically what can we know, to computational complexity, and that means how quickly can we know it? This is something which is now sort of reconsidered in that context of algorithms validation. So let me close with the following summary. Why do we experience a paradigm shift in human thought? And I think the bold title should refer to the following points. First, knowledge has been created or discovered by human brains since modern humans appeared on Earth. So human brains were the driver of the knowledge production. Tomorrow, self-learning machine will do that. They will have access to data and they create that knowledge. And unfortunately for us, these machines might know something which we never be able to understand because it's for us too complicated, too complex to store. So high complexity models can be predictive, but cannot be understood by human brains due to the limitation of storage capacity. Algorithms model posterior of unprecedented complexity that will never be understood by humans. I just made this point. And machine learning empowers these algorithms to infer, for example, personalized conditional theories of individual humans that generalize, for example, over life circumstances. That's something we never even considered. We never even thought that these are theories. But I don't see any reason why that is not a theory when you condition on my genome and then give me the best possible predictions of how I should conduct my life, given I have set the right, I have determined what kind of values I like to have as a guidance for these predictions. And fourth, the predictive power of data-driven models has to be validated, even if no humans will ever be able to understand these models. That is a real paradigm shift in human thought, because so far humans decided whether a model was useful or not. With these examples which I gave you, I hope you got an impression in which direction the train is leaving and what the challenges are. And I must summarize, I find it the most exciting times in my academic life so far. Although I might not understand the full dimension of it, and it's up to future generations to sort of work it out and to adapt it to how we live. It's a great tool to actually have a broader view in the future. And with that, I'd like to thank you for your attention.
Thank you a lot, Professor Buhmann, for this fascinating talk. In particular, the final conclusions, I think, really tell us that part of our research directions trying to make big data understandable for humans are possibly going in the wrong direction, in the sense that we have to validate the results of big data applications rather than just trying to understand what the logic is in behind. Are there any questions from the members in our discussion group? Then let me pose one question. If all these new findings are applied in digital health, how is it possible to teach professionals in the health sector to really handle the new technology possibilities?
I believe you have to adapt it to the setting. You know, you don't have to be an auto mechanic and be able to handle a car quite well. In particular, you handle the car in the setting of driving quite well. If you use these prediction tools, what a medical doctor, and that's actually what we try to do now in the bachelor education of medicine at ETH, but also with master courses in conjunction, in collaboration with the University Hospital in Zurich. What we try to do is we try to enable the doctors to get a feeling what the power of these predictions are. Now, even a computer scientist who has set up a deep neural network relies on the fact that the optimizers and the randomization chosen is done properly by these software packages which you get from Amazon and other providers. So we are not so far away. The challenge to actually get an answer, and then by simulation and slightly different analysis of your data, get an idea how stable these answers are, that's something which everybody can do. And don't forget, the medical doctors actually have a fairly sophisticated qualitative judgment of what's going on in these settings. What they don't know is, or what is far poorer established, is their introspection capabilities in what is going in their heads when they actually make a diagnosis, a prognosis, and commit to a therapy. So I stopped asking my doctor what he is thinking when he is starting the analysis, because I know that his introspection capabilities are far inferior to his experience, which is actually not in the rational setting of his thinking, but in the sub-rational experience crunching. And in that sense, this is quite similar to what we have in deep neural networks. So controlling the process is absolutely mandatory for the user. Understanding it in detail would basically mean, if you request that you are limited to the low Kolmogorov complexity modeling world of reality. And we all know that this is not true. It's not even true in astronomy, where you have fairly, let's say, from a descriptive point of view, fairly simple individual players, the stars. But their enormous numbers is what makes it complicated.
Okay. I think this is very understandable to me. Maybe I would like to ask you one or two further questions in private at a different occasion, but I don't want to take the floor with my perspectives. But there was one question already in the FNA concerning how we manage the problems that usually access to data. I mean, I'm translating a little bit the original question, that access to data is a huge problem in many sectors where personal data are involved.
Yeah, you have to, so privacy concerns are very important concerns, but I would like to actually make a distinction. So from my point of view, there is an innate desire for privacy built into our behaviors when it comes to all issues related to sexuality and reproduction and organization of our core societal groups like families. My drive to keep my genome private is more coming from the fact that I do not want third-party players to exploit that knowledge to my disadvantage. But that is something you can legislate. Nobody has to organize an insurance company business in a competitive way so that exploiting this type of side information is of advantage. We can organize societies in different ways. So I think the technology forces us to rethink all elements of our societal life. And what I'm occasionally say is, we have been naked and we didn't bother because we didn't notice. But now with this technology, all of a sudden we see that we are all naked and unprotected. And so we have to rethink, parallel to the development of the technology, how we actually rebuild the basic mechanisms in our society in such a way that the outcome is informative and reliable with respect to our values. So the question with respect to the GDPR, for me, the GDPR is a first attempt to have legislation in that direction. Whether it's the final answer, I'm pretty sure it's a no. No, we will learn a lot about this. And in particular, the understandability of algorithms, I think, is a myth. Frankly speaking, I don't believe in it. If it's so simple that I can understand it, maybe it's not solving the jobs in those areas of science where we have no quantitative modeling attempts, like in health, like in society, like in finance, in many other areas. The complexity was so high and it was not random in a sense of a gas. So that's the issue here.
Yeah, thanks a lot. I can just add two remarks. Those lawyers I know from Brussels dealing with the GDPR topics, they are all convinced that it was not an optimal situation to create a new legislation, because the understanding of how the legislation should be, they are aware, is much less today than it was 20 years ago. And I think this complies exactly with what you say. We have to rethink how we organize our society based on the new possibilities before we then think about really optimal solutions on privacy, set the law and legislation on that. And the other thing I think is also that we have been naked, we didn't know, is part of this sociological debate I'm following. That people say privacy has never existed anyway. It's
Sure. If you look at in the biography of Oppenheimer, how much investment in data collection the FBI at that time invested, then you see what has been possible. It just didn't scale. The problem is now it scales for everybody of us, and that's why it's destabilizing. And now we have to rethink in a fundamental way what this technology makes with our lives, what it transforms. And then we can invent new mechanisms to get control back and to stabilize it for the future. Because it's very clear, this technology, I believe, is the only technology which will solve the fundamental problems, if there is a solution at all, of humanity. How do you want to manage global warming at a global scale? You see, local decision-making will not work. In particular, not with humans who make the decision now, but future generations have to pay.
I was just informed I have the pleasure to continue a little bit the debate with you, because the panel is not fully ready. So I take the possibility to ask you another question. What I'm observing, and what was a bit referring to in my introductory note, also it also had possibly other motivations as well. But what I'm observing is, having grown up as a mathematician, doing my PhD in pure mathematics, and then having worked a lot in computer science, in industrial contexts, performance management and the like, and later on in business informatics, I'm observing that it's collaboration. I mean, all these people are very close to each other. Econometrists, computer scientists, mathematicians, for example, in the topic of causal machine learning, to identify causality of interventions and so. I mean, but it's so difficult to get these people to collaborate. Not only they're using different wordings, but they also are envious of each other. That the others get more attention. The mathematicians are always telling me how unfair it is that computer scientists are now taking the solutions they have developed 15 years ago, and they get also applause. I mean, how have you experienced your collaboration across disciplinary boundaries, which you obviously did a lot?
Yeah, it's a sociological problem. I, for myself, remind me then when sort of the gull is getting active. I remind myself that society pays me to produce knowledge. And you should actually keep in mind that it's, in some respect, an inherently schizophrenic business. Up to the point where you actually have the results, you try to make it as general as possible so that it's actually acceptable as general wisdom. And after you have received the results, you invest every effort that nobody forgets that you did it. Now, science is not a business to become famous. It's a mechanism. The fame is a mechanism to sort of motivate people. But that is, if the mechanism is not giving me optimal results anymore, I should reconsider the mechanisms. And I think we have a very good life. And if I read a little bit the sort of popular stuff on the Library of Alexandria, you see already 250 years before Christ's birth, before our time counting, people got the liberty to produce knowledge. They also had a servant for that. And the only justification was to have insights. And the insights then were used by the rulers to organize society. If you live in that respect, it's very clear that that you should be gracious to those who pay attention to what you have done and pay tribute to it, but all the others play the same role. It's the knowledge which has to be fostered and not your personal fame. And this is sometimes actually confused, and usually it's counterproductive. The more you push for it, the less you will get. That's also a human mechanism to keep sort of a balance between different aspects.
Thanks a lot for your great talk, and also I think this was great final word you said on a very important topic. We are now ready to switch to the panel, but did I understand it correctly that you are going to answer a few questions in the chat as well in the next minutes? Are you able?
Yeah, I can do that, yeah.
That would be great. Thanks once again, and I think representing all the others, I give my applause for this fantastic insights you gave to us. Thanks a lot, and
yeah, thank you very much for your attention. Yeah,
very glad that you were with us.
Okay, great.
Thank you.